Okay, so if you take a look, 422, we're still talking about probability. We're still talking about multiple events happening rather than just rolling a die or just flipping a coin or something like that. And yesterday we talked about area models, which we're going to start with. We'll review that right away in this first problem. But today then, we're going to look at using a tree diagram, okay? And that's kind of the next step. That's if we have more than two things, then that's where we're going to go. So if you take a look at problem number 1 here, 464, your teacher challenges you to a spinner game. Okay, so here's the two spinners. You spin the two spinners with the probabilities listed at the right. Okay, so this, by the way, when you look at this right here, down here, where it says P of I, with I in that stands for the probability of I. Okay, the probability of landing on the I portion is 1/2, because it's half the circle. The probability of U, in this case, they're telling you is 1/6. They're telling you that portion is 1/6 of the circle, and probability of landing on A is 1/3. Okay, so they're giving you the probabilities. So it says the first letter will always come from spinner number 1. Second letter comes from spinner 2. And if the letters form a 2-letter English word, you, the student, wins. If it does not form a word, then I win. Okay, then the teacher wins. Okay, so if you went through and you do the spinner. So now, notice in part A, it says, are the outcomes for spinner 2 independent? Okay, this is similar to what we were talking about in the homework. Spinner 2, spinner 1, are those independent or dependent? What do you think? Does what you get on spinner 2 have anything to do with what you got on spinner number 1? No, right. They're completely independent of each other. Okay? So for part A here, when it says, are they independent? Yes, they are. They are completely independent of each other. It does not matter on spinner number 1, whether you get an I, a U, or an A, you still have the same probabilities of getting a T or an F on spinner 2. Okay? That doesn't change based on what you got on spinner number 1. So now in part B, it says to make an area model. This is going back, and this is the review from yesterday, of the sample space and find the probability that you're going to win this game. Okay? We're going to take a look at this. And so, two things. You got spinner 1 and spinner 2. That's why an area model works really, really nicely. So down here, I gave you kind of a chart. Quick question, by the way. I built the chart for you. Why is it a kind of a 2x3 or a 3x2? Why is it those dimensions? Yeah, Aubrey?
Because you have 3 on spinner 1 and 2.
Because you got 3 options on spinner number 1 and you got 2 options on spinner number 2. That's exactly the reason. Okay? If I had 3 options on each, then it would be a 3x3 chart. Okay? So I'm gonna put spinner number 1 up top here. Spinner number 1. And we'll put down the different probabilities and the different letters here. So for I, probability is 1/2 of landing on that. U, probability of 1/6. And A has a probability of 1/3. So there's spinner number 1 on my area model. There's what could happen on the first spinner. Then we go off to the side, and it doesn't matter which side. But I'm going to put spinner number 2 over here. And the 2 options on this one are either T or F. The letter T has a probability of 1/4. The F has a probability of 3/4. Okay. All right. So there's the chart. There's the area model. Now we go through and we take a look. All right, let's actually calculate the probabilities of all these different options. So if let's say I start up here in the upper left-hand corner, okay? The probability of an I and then a T happening in this spinner game. We've got a 1/2 probability of an I, 1/4 probability of a T. What do I do with those probabilities? What did we say yesterday? We multiply them. Yep, we just multiply the 2 probabilities. And remember, when you multiply a fraction, numerator times numerator, denominator times denominator. So the probability of that happening is 1 out of 8. 1/8. What I want you to do real quickly is fill out the other 5 boxes. Okay, find the other 5 probabilities for this spinner game. Multiply the probabilities, put that in the box. And then we'll discuss whether you win or lose or what that kind of stuff. let's take a look, see how you're doing here. So if we multiply these probabilities together, probability of U and then a T on the second spinner, multiply those, we get 1/24. Probability of an A and then a T, we get 1/12 when we multiply those. Probability of an I and then an F, we end up with 3/8. A U and then an F, we get 3/24. And finally, an A and then an F, we get 3/12. So there's your probabilities. Now, it says in part B as well, let's take a look to see what's the probability that you, the student, wins versus me winning the way this game is set up. Okay? So remember, you, the student, you win if when you do spinner 1 and spinner 2, it ends up spelling a word, a two-letter word. So in this case, we've got an I and then a T. It. If that happens, there's one scenario where you would win. Okay? You'd win on that one. How about a U and then a T? No, that one I win. Okay? If it ends up on a U and then a T, then I win in that case. A and a T, we got the word at. There's another option where you would win. Here we would have I and then an F. We got the word if. There's another scenario where the student would win. Then we've got UF, nothing there. And then finally AF, also nothing there. Okay? So that doesn't work out. So there's 3 different scenarios where the student wins, 3 different scenarios where the teacher wins. Okay? But they're not all the same probabilities. So just because it's 3 and 3 doesn't necessarily mean that this is, an even fair game. We're going to look at that in a second. So let's take a look at those probabilities. What do I do, by the way, with those 3 probabilities I circled? How do I now calculate the probability that you, the student, wins? What do I do with those? Was it?
Yeah.
We add them up. Yep. If you have more than one way to win, you add up the 3 different ways that you have to win, which this one's going to be a little bit more complicated because when we add fractions, what do I have to have? Common denominators. So what's the common denominator of 8 and 12? 24. Okay, so let's change all of this. So 1/8, that means in order to get the denominator to 24, we got to multiply by 3. So we're going to multiply both numerator and denominator by 3. So we now have 3/24 plus, next one, we're going to multiply by 2. So we get 2/24 plus, last one we got to multiply by 3, I get 9/24. If I add all those up, we end up with, what, 14? Do that right? Yeah. 14/24. So there is the probability that you, the student, will win. If we were going to play 24 games, okay, if we did this game 24 times, in theory, you should win, or if we did the spinners 24 times, you should win 14 out of 24 times. Which now leads to hopefully a fairly common sense question. Part C, is this game fair? For both sides playing the game? No, because you have a better chance of winning than I do. You've got a 14 out of 24 chance. I've only got a 10 out of 24 chance, and therefore not fair that you have a better chance than I have. Okay? And so there's kind of an idea right there. And so if we played the game 100 times, you would probably win more often than I would. Okay? Or at least you should, based on those probabilities. So now, let me ask you a question on this one, because this is where we're now going to transition into the next part. What if I had a third spinner? What if there was a third spinner with some more letters on it? Could I use an area model to create a chart? Or let me rephrase that. We can't use an area model. Why not? Why does it now get much more complicated? What's the issue? If I had a third spinner, where would it go? And hopefully you can visualize this. The reason why area models work really nicely when you're dealing with 2 things is because you've got 2 dimensions. You've kind of got a length and a width. You've got 2 sides of a rectangle. If you technically would have a third spinner, you'd have to now go to like a 3rd dimension and start creating little kind of floating probabilities in all the different 3-dimensional boxes and things along those lines. And heaven forbid you then go through and have a 4th spinner, Now you got to try to figure out how to draw that. And that's that transition into when an area model works really well. This is one of them. Okay? I would 100% use an area model for this every time. Versus now we're going to take a look at at a tree diagram. Okay? And so if we take a look, I'll go to the next page here. If we take a look at the tree diagram, so same exact problem still, but now we're going to reorganize it. Okay, notice it says Sinclair wonders how to model the spinner game using a tree diagram. So he draws the diagram at the right, which we'll take a look at in a second. Sabrina says that can't be right. This diagram makes it look like all of the words are equally likely, okay? Which it does, right? Makes it look like if you get the word, so option, this basically right here is spinner number 1. You have 3 things that could happen, an I, a U, or an A. If the first one is an I, then you still on the second spinner could get a T or an F. That's why both parts are still coming off of there. If the first one is a U, second one could still be a T or an F. If the first one's an A, T or an F, still have those options. But, like I said, it does look like all of those things are equally likely. Okay? It looks like IT, IF, UT, it looks like they're all about the same. And they're not. We know that from the game, that they're not all equally likely. So the question is, how do I go through and how do I fix it? Okay? And here's the idea of what we're going to take a look at. I'm going to kind of work my way through. So I think this is on the next page, yeah. So if you're taking a look at this diagram right here, okay? You've got, here's the I, and then like I said, T for the word it. I and then F for the word if. U and then T, and so on and so forth. How do you think we can show the different probabilities so it doesn't look like they're all the same? What do you think? Where could I put those? Where could I put those probabilities? Here's what I want you to keep in mind. Let me go back for a second. Where did I put the probabilities with the area model? Was it? Somebody said it. She was right, too. Right by the letter. Notice, in the area model, it's right by the letter, the probability. Same exact idea here. We can put this is called the tree diagram because you've got all the different branches, is kind of the idea. We can put those probabilities right by the letters. Okay, so when you go through and you build a tree diagram, whatever the first situation is, in this case it was spinner number 1, those are the different branches, all the things that could happen. Okay? I, U, or A. And then off of each of those branches you put this options for the second one. T or F, T or F, T or F. And if we take a look, here's what this should end up looking like. Okay? Go ahead and fill those in on your tree diagram. Okay? Go ahead and fill those numbers in. The different probabilities. So probability of an I was 1/2. Probability of a U was 1/6, and so on. So it's still the exact same information, just organized in a different way. How'd they get the answers in green, by the way, on the end? Where'd like that top 1/8 come from? Based on the tree diagram. Holden, where'd it come from?
The table or whatever.
Let's say we didn't have the table. Let's say this is all we had. Carter?
Came from multiplying like the 1/2 and 3/4 or 1/4.
Yeah, it's just basically you're following the tree for the most part. For example, if I wanted this word right here, this IT, well, it came from I and then T. So we just multiply the probabilities along that track, if you will. 1/2 times 1/4, that's where the 1/8 is coming from. If it was IF, the word if, then we go through and instead we would multiply, we'd go through I and then F. those two probabilities. That's where the 3/8 is coming from. So these are the same final probabilities that you had in the chart. Okay, same exact probabilities, and then we do it the exact same way we were before. All right, well, which one of these would you win? Any of the words that have the final letters? Then you can go through and calculate and add up the probabilities. Okay? One final thing on this one that I want you to take a look at, and that is, if I had a third spinner, now all you'd have to do, and we're not going to do this, but now all I would have to do is say maybe the third spinner had another 2 letters on it. Okay, now I go through and I add to the end of each one of those. And now I can add a third spinner. And then if I wanted a fourth spinner, I could go to a fourth phase and add some more branches. That's the basic idea, is you just work your way through. The first set of branches represent the first thing. The second set of branches then represent the second option, and you can just keep expanding it from there. Okay? Let me stop for a second. Does that make sense? The idea that we can just keep adding branches. And that's why 3, 4, whatever, it doesn't really matter. You have an option in order to organize it. Okay, so this was kind of the introduction to what is a tree diagram, how do they work. Now, here's what I want you to do. Let's take a look at this next problem here. The rat race problem. Okay, and I've got the picture in your packet, but here's what's actually going on. So Ryan has a pet rat, Romeo, that he boasts is the smartest rat in the county. Sammy overheard Ryan at the county fair claiming that Romeo could learn to run a particular maze and find the cheese at the end. I don't think Romeo is that smart, Sammy declares. I think that the rat just chooses a random path through the maze. Ryan built this maze with the floor plan shown at the right. In addition, he placed some cheese in an airtight container, so Romeo couldn't smell the cheese, in room A. So now we're going to make an assumption here. Suppose that every time Romeo reaches a split in the maze, it is equally likely for him to choose any of the paths. Okay, so if there's 2 paths, 1/2 and 1/2. If there's 3 different paths, each one would be a third. If there's 4 different paths, each one is a fourth, has a probability. Okay? Choose a method and calculate the probability that Romeo will end up in each room in a sentence or 2. Explain why you chose that method. Okay, so let's actually work our way through this, which, there's the diagram that you have right there. Let's actually use this as our tree diagram, basically. It's kind of already built for us. So option number 1 here, rat comes into the maze. What's the probability that he goes this way? 1/3, because he could go up, he could go straight, or he could go down. So he has 3 different options right there, which means I'm going to put right here 1/3, 1/3, and 1/3. Okay? Those are the probabilities that he either goes up, down, or straight into the room A. All right, so let's say that he goes up. Now he gets to kind of the next fork in the road. What's the probability? 1/3 again, because again, he could go up, straight, or down. So each one of those has a probability of 1/3. Okay? Well, what if Romeo the rat, goes down instead? What's the probability at this point that he takes each one of those paths? Not 1/5. How many paths does he have? 2. So 1 out of 2. He's going to take 1 out of 2 paths. So this one will be 1/2. That one would be 1/2. And now that we've got kind of the probabilities all set, now we're going to take a look and actually calculate what's the actual probability that this path is the way he goes, or this path, and then we can total up the probabilities of ending up in room A versus the probability of ending up in room B. Okay? So if we take a look, let's do some calculations here. Let's actually, probability he goes up and then up again, all the way to the top. 1/3 times 1/3. This probability, I'm going to put it in a different color here. This probability is 1/9 that he takes that. Okay? That he takes that path. Probability that he goes up and then straight. 1/3 and 1/3 again. Probability once again of 1/9. 1/3 and then down into room A. Same thing again. Another probability of 1/9. Probability just goes directly into room A. Just goes straight ahead. It's just sitting right there. It's just 1/3. So we'll put that in there. Last two options, if he goes down and then back up into room A, 1/3 times 1/2 gives you a probability of 1/6. And same thing if he goes all the way down to the bottom. You get a probability of 1/6 of choosing that path. So now if we put this all together, now we've got all the different probabilities of every different way that he can go. Now we can calculate what's the probability he actually ends up in room A versus the probability he ends up in room B. Okay? Is it just luck that he's getting there, or are there a lot more ways to get to one room versus the other? A lot better chance. And now we're right back to what we were doing. Add up the probabilities in each room. Okay? So, if we do that, let's do that in a different color here. So for room B, notice there's 1, 2, 3 different ways that he could get into room B. So I need to add those 3 up. In this case, again, common denominator. What's the common denominator of 9 and 6? 18. Okay, so in this case, the top one, the 9s, we're going to multiply by 2. So we have 2/18 plus another 2/18, and then 3/18 for the bottom one. 2/18, 2/18, and 3/18. For which one? The bottom one? Oh, just because we're multiplying by 3. So now if we add those 3 up, we end up with 4 plus 3 gives me a total of 7/18 is my probability of ending up in room B. Okay, this rat Romeo has a 7 out of 18 chance of ending up in room B without even, I'm not even going to bother adding up these other ones. The 9, 6, and 3. Just in your head, what's the probability then that he ends up in room A? Or does it have to be? What is it? It's got to be 11/18. If out of 18 tries, 7 of those he's going to end up in one room. The only other place he can go is the other room. And therefore, this has a probability of 11/18. Okay? Which means, by the way, if we go back to the actual problem now, there's our probabilities. If I go back to this actual problem, Sammy said that she just thought he was choosing a random path and luckily ending up in room A where the cheese was. Is she right? Based on our probabilities? Which one has the probability of the greater chance of which room are we going to end up in? Yeah, room A. More chances than not, you're going to end up in room A, just randomly end up there, versus being able to train the Romeo the rat to get there. So she might be right. We don't know for sure. But probability says better chance of ending up in room A than there is in room B. Okay? Let's take one more look at this one. In part B here, if the rat moves through the maze randomly, out of 100 attempts, how many times would you expect to end up in room A versus room B? If there's 100 attempts, how can I use my probabilities to calculate that? What do I do? Explain the math to me on this one. There's an 11 out of 18 chance for room A. How do I figure out of 100 that I would expect to end up in there? What do we think? What do we think? Couple of ways we can do it. One way we've been kind of working on for quite a while. What do we think? Ellen, any ideas? If I know that there's an 11/18 chance of ending up in room A, and I did this 100 times, how could I do that? What math can I set up?
I'd say I did 11 divided by 18 divided by 100.
Okay, yeah, so option number 1, you could take 100, the total number of tries, and then just multiply it by the probability. You say, well, if 11 out of 18 times you're going to end up in room A, let's just take that probability times 100 and see what we end up with. Perfectly fine. Okay? So option number 1 here for part A, or for room A, we could take the probability of 11/18, multiply it by 100 runs, and what did you get, Ella?
61.1.
Okay, so we'll say 61. We'll round it to 61 as a whole number. So approximately 61 times you would expect that the rat ends up in room A just based on probability. Which means, by the way, you could do the same thing for room B. You could take 7 out of 18, the probability, multiply it by 100, or in this scenario, if you know you've got 61 times in room A and there's 100 times total, you could also just figure out what's left. End up with 39 times. Now, one other option. As a matter of fact, I'm gonna leave it at that. I'm not gonna give you the other option because I like that one. Okay, it's gonna lead into something we do in a couple of sections, that idea. If you take the probability times the number of trials, you can get. Here's what I expect to happen if we did this 100 times. Now, does that mean this is what will happen? No, but just based on the probabilities, we're expecting that would be approximately what would happen as you go through and you run this trial. Okay? Here's what I want you to do. Here's a practice one for it. Go to the next page. Okay? 467 here. You're going to have a chance to do this on your own now. Okay? Here's your practice problem. Always skeptical, Sammy says, if Romeo really can learn, he ought to be able to figure out how to run his new maze that I've designed. So her maze is at the right. To give Romeo the best chance of finding the cheese, in which room should the cheese be placed? Okay, choose a method and then figure out which room. What I want you to do is what we just did, and again, assuming that every kind of fork in the road is equally likely, I want you to go through looking at that picture, put the probabilities in, and calculate what's the probability of landing in room A versus B versus C. Okay? I'll give you a few minutes to work on that. Put the probabilities in and do your calculations. Remember, multiply your probabilities to get kind of the final path, and then add those probabilities of all the different rooms to get your final answers. There's the probabilities if you're kind of wanting to check to see where you're at. There's what you should have to at least get started. There's in red are the different probabilities of taking each path. In blue then are the multiplied probabilities. One thing to notice, especially down here, So 1/2 and 1/2, you're either going up or down it. When you get down to this point, it's an up or down decision, and then you get to the next fork in the road, and again, you're either going up or down at that point as well. Okay, so you've got multiple 2 options. Okay? And then again, multiply the probabilities of each path. Mr. Coonan,
Was he smart?
we're finding out. We're going to find out where to put the cheese.
Yours is different.
What?
than the one.
This is the one out of the book. This is the second one out of the book.
Oh,
We already did the first one.
I get this.
Yeah, we're doing the second one. Get your printing issue fixed?
Kind
Okay.